Okay, so we're going to be looking now at the final sort of topic within this chapter of the textbook, but we're going to split it into two parts because it needs a little bit of practice, I think. And that is applying this elastic energy concept to actual problem solving style questions. So to start off with, I've got the same scenario as in the previous session. You've got an object hanging from the ceiling on a spring, and I hold it in position at its natural length, and I let go and it drops, and eventually after some amount of time the object comes to rest. The question now is, well, we know what happens in terms of the energy transfer. The potential energy gravitationally that is lost will be converted into elastic potential energy. But the question is now, can we find a formula that describes how far the object will fall in total? So from that resting stage where I'm holding it and I drop it, it drops and bounces up and down a bit, and now it's at a new level. How far did it drop? So that's the question. So see if you can come up with something. You know, give me a formula H, let's say H, or you could even call it X. Maybe let's call it X for less confusion. So that extension, what is it? It will be some function of, you know, lambda, the mass of the object and natural length. But what is it? Have a think. Think about potential energy, think about elastic potential energy, and see if you can derive it yourself. Okay, so in this case, first of all, let's just get kinetic energy out of the way. We don't need to consider it because it started at a speed of 0 or a velocity of 0, and it's ended at a velocity of 0. So then we think about potential energy, and how much is it lost? Well, if we say x is the distance it's dropped, which is what we're trying to work out here, then it's going to be the mass times gravitational constant g times the height that it's gone down, or in this case x. The elastic potential energy gained is just going to be the formula, right? It's going to be modulus of elasticity x squared all over 2 times natural length. So therefore these two are equal. Where one has lost, the other has gained, and that tells us that mgx must therefore be equal to lambda x squared over 2l. Let's cancel an x from both sides, multiply by 2l, divide by lambda, and we end up with the following expression. Let's get rid of that. X is going to be equal to 2 mgl divided by lambda. Okay, so well done if you managed to get that. So we can see now what it depends on. How far an object on a spring drops ultimately depends on 3 things: the mass of the object, and then 2 properties of the spring, its natural length and its modulus of elasticity. Okay, so now that we've got the elastic potential energy concept, let's add that to our work energy principle equation. So if you remember, the way I prefer to express it was this, as a sum of changes. So the sum of the change in kinetic energy plus the change in potential is the same as your work done, which is easily expressed as work in minus work out. Now, before we knew about elastic potential energy, we may have just included it within this work in, work out. But now, because it's got this special designation and its own formula, a bit like PE, we're going to include it on this left-hand side now. So we're going to now change this, or update this to make it even more accurate, or maybe not more accurate, but more specific, I suppose. And it's going to look like this. Okay, so we're going to use this version now. That's not to say the previous one is wrong, it's just that previously we would have, as I said, included elastic potential energy somewhere in here, we would have said, oh, that's work out. The work's been lost somewhere to the system, but we haven't thought about where. Well, we know where now. It's gone into the elastic potential energy of the spring. Okay, so that's the new version, and that's what we're going to work with. So let's look at the first of our 3 examples. Light elastic string, natural length 1.6, modulus of elasticity 10, has one end fixed at a point A on a smooth horizontal table. Okay, so this is a horizontal question. And a particle of mass 2 kg is attached to the other end of the string. The particle is held at the point A and projected horizontally along the table with speed 2 meters per second. Find how far it travels before first coming to instantaneous rest. Okay. So, effectively, let's do a before and after, I suppose. So these are my sort of before and after pictures. So in the before, the object was at A with its mass of, let's just say mass here is 2, and it starts at a speed of 2 meters per second, right? That's its initial velocity, and in the after, it comes to rest, so it's now 0 meters per second. But this string is here, and presumably it's been stretched, right? So it's got some natural length, which in this case is 1.6, and it's also got some extension to it. We don't know what that is. Note that, yeah, it says here instantaneous. This object, which has been projected to the right, only instantaneously comes to rest. It's going to bounce back to the left again. So this after image here is just a moment in time, an instantaneous moment in time. Object's going to go flying back to the left. So this question is quite nice actually, because I think you technically wouldn't have had to know about EPE to answer this, because as you know, when it comes to rest, that's when the tension balances with the no, actually I take it back. I think you do need to use EP for this. Never mind. Okay, so let's use it. So we've got our nice way of writing it: change in kinetic, change in potential, plus change in EPE equals work done, work in minus work out. In this case, there's no additional work in or work out, right? Because the object's projected, and then at that point it's all hands off. No one's touching the ball, no one's prodding it, no one's applying any more forces. So it stays at 0 in this case. What is the change in kinetic energy? In this case, it starts with kinetic energy of a half times 2 times 2 squared. So that's going to be 4. And it ends with kinetic energy of 0. So it's lost. Okay, so we've got -4 kinetic energy. Then potential energy, well, this is a horizontal problem, so that's nice and easy. Nothing's been lost or gained. The change in potential energy is 0. Really, PE in that context, maybe it's better to call it GPE, because PE by itself is a bit too generic. I'm going to continue writing PE and just assume that by default we're talking about gravitational potential energy. If you want to write GPE to make it a bit more or a bit less ambiguous, that's probably a good idea. EPE then, what did we start with? Well, there was no elastic potential energy at all, because the string was actually taut. I mean, the string is still here in the image, but it's completely loose. Effectively, it's bundled up, it's loose. There's no EPE at all, so it's gained some. How much has it gained? Well, it will have gained this amount, x squared times lambda over 2L. So let's add that. That's going to be lambda x squared divided by 2 times the natural length, which is 3.2. So working with that, then do a bit of rearranging. You'll end up with x squared equals 4 times 3.2 over 10. which gives us 1.28, and therefore x is equal to, and I square root it, and I get 1.13 roughly. So that's our x. How far has it then travelled before coming to instantaneous rest? Well, it was this natural length, 1.6, plus the x. So we have to remember to still add that 1.6 on, which we can do in our heads. That's 2.73 to 3 significant figures meters. Okay, that's it. Okay, so this problem here, it's a bit similar to the starter question on the first slide, but a little bit more tricky. We can't directly use that formula we came up with. What was it? The 2mgl over lambda. Reason being, in this case we've got an object on an elastic string, but it is released not from the natural length, but from a point where the string is completely taut. Let's just read the question first to make sure you know what I'm talking about. So we've got this mass of 0.5 kgs attached to an end of an elastic string, but it's at this point O here, right? That's where the object is. Let's say the object's in green, and you've got this string, and it's it's loose. It's a loose string effectively, and it's just hanging there, or it's being held there. Okay, and then the particle is released. So let's do our before and after. So this is before, and this is after. This object is released, and that string is going to become taut. And not only that, it's also going to stretch a little bit until it gets to a point where this object, this mass, reaches its greatest point of displacement from the ceiling, effectively. So that's the question: is what is that distance there? What is that? So first of all, we're going to think about what's going on with the velocities. At this point here, the velocity is 0 in the before, because it's dropped from rest, and at this point here, the velocity is also 0, right? Because the point at which it reaches a maximum displacement, the velocity is 0, much like if you throw something in the air, the greatest height that it reaches will be associated with a velocity of 0. So that we get for free, the velocity is 0. And now let's split up this distance into its two components, and they are going to be the natural length of this string, which is 2, and some kind of extension, which we'll call x in this case, right? So our answer for O is effectively going to be x plus 2, right? So our job is now going to be to find x. So what other information do we have? We also have that the mass of the object is 0.5, and the modulus of elasticity is 19.6. Okay, cool. All right, so let's consider energies. So right over here, as before, change in potential energy plus change in kinetic energy plus change in elastic potential is going to be 0. The change in kinetic energy, again, is 0, much like previous examples. The velocity started at 0 and the velocity ended at 0, so there's no overall change. The change in potential energy, well, it's lost some, right, because it's fallen down. It's fallen down a distance of 2 plus x, and then we multiply that by mg to get the potential that's lost. So m is 0.5, so we get a half times 2 plus x times g, and in fact it's going to be minus that because it's a loss of potential energy. Okay. And then the elastic potential energy, well, while it was falling that first 2 meters, there was no potential energy elastically, and in that final x meters, it started to gain some. It slowed down, its velocity went to 0, its potential was being used up, its gravitational potential was being used up, but the elastic potential has increased, but in that range there. So that's an extension of an x. We're going to use the formula lambda x squared, which gives us 19.6 x squared, all over 2 times L, which in this case is 4. We might as well cheat a bit actually, because this 19.6, that's clearly 2 times g, which will make things cancel out a bit nicer. So let's just write it in. That's 2g there. So then divided by 4, we can just turn that into a half g squared. Okay. So that's equal to 0. Let's multiply by 2 and divide by g. So we'll get minus of 2 plus x plus x squared equals 0. That gives us minus 2x plus x squared. And we've got a nice, fairly simple looking quadratic. Although, yeah, we don't have the 2 there. Okay, x squared minus x minus 2. Let's solve it. I'm just going to go over here. In fact, that one I think we can do by inspection, can't we? So it's minus 2 and plus 1. Okay. So we get 2 solutions for x. X equals 2 or equals minus 1. Those are the 2 possible values for x which solve the energy equation. Now it's always interesting to think about why we get multiple solutions and why some of them might be invalid. Now hopefully it's obvious to us that we're going to go with the 2. But let's just ask ourselves for a moment, why are we getting a random, well not random, but why are we getting an unnecessary solution? Why are we getting this negative 1? So if you think about it, these formulas that we've used here, when are they actually valid? So for x being negative or positive, this kind of makes sense. Potential energy, you can say it increases or it decreases, and that would result in a positive or negative potential energy. With the elastic potential energy, it less so makes sense, right? Because with a string, when you stretch it, you have EPE, elastic potential, but when you compress it, you can't actually compress a string, not elastic string. It just becomes slack. So a negative x corresponds to an attempted compression of the string, which is going to fail. You're not going to get this half gx squared. You're going to get 0. So this false answer is an artifact of the fact that our formulas work for negative numbers, as in they work in the sense that I can put a negative number in and get an answer, but they don't actually give me the correct answer. So if that were the case, minus 1 would be a possible solution, but it's not really, because this formula in particular is not an accurate model for when x is negative. So anyway, we're going to disregard this because we know our answer should be positive based on our understanding of how things work when you drop them from strings. So x is 2, and we get our final answer, which is going to be 4. Okay, and let's look at our final example. We've got a light elastic spring. Natural length is 1. Modulus of elasticity is 10. One end is attached to A. A particle of mass 2 kilograms. Attached to the other end, held at a point B, which is 0.8 meters vertically below A. Did I say 0.2? 0.8. The particle is projected vertically downwards from B with a speed of 2 meters per second. And there's presumably an elastic spring in this case here, and then there's our particle attached there, and it's projected downwards. So just to be clear, this 2 meters per second, if I held it at rest in that spring, so in this case it's being compressed, isn't it? Because the natural length is 1, but it's at 0.8, so it's being compressed. If I held it there and let go, the initial speed is going to be 0, but it will instantaneously increase, so it will actually start to speed up. But at that exact moment it will be 0. So this 2 meters per second, this is entirely due to an additional force or an additional projection that took place. It's not going to take place anymore, the force is gone now, but for whatever reason that ball was given an initial speed of 2 meters per second, regardless of the fact that there's a spring there. So what this means is, for this particular problem, we're going to take into account many things, or the 3 main things, which are potential energy, both gravitational and elastic, and now also kinetic energy as well. So find the distance it travels before coming to rest. We are interested in this mysterious distance here, where it comes to rest here at a velocity equal to 0. So I think it's worth always breaking up this mystery distance into components that then create a position where you can see the natural length. Let me rephrase that slightly. We should mark the natural length effectively on our diagram and then fill in the distances either side. So the natural length is going to be at a point around about here. Remember, it's 1. So that means you've got a distance between where the ball starts, or the object, and the natural length of 0.2. And now we're just going to call this extra mystery distance, this extra part, we'll just call it x. Okay, and then we'll use that x as an extension. Okay, so let's think about the before, let's think about the after. We're going to use the change in potential energy plus the change in kinetic plus the change in elastic potential. So first off, what's the change in potential energy? Well, it started at whatever amount, let's say 0, and it has now decreased by mass times the distance times g. The distance is x plus 0.2. The mass is 2, so that gives us a change of 2g x plus 0.2, where x is that unknown. Change in kinetic energy. Oh, and by the way, this is a negative number. It's decreased because kinetic has gone from half mv squared, which is a half times 2 squared, so that's 4, and it's decreased to nothing. So 4 minus 0 gives us 4. And then finally, the elastic potential energy. So this one's the more complicated one. Initially, its displacement or its extension is 0.2 compressed. So we're going to do final minus initial, aren't we, to get difference. So let's actually do the final. The final is going to be an extension of x times lambda all over 2L, which is 2. And then minus its compression extension initially, so that's 10 times 0.2 squared all over 2. So if we simplify that, we get 5x squared minus 0.02 times 10, 0.2. Okay, so that's our change in elastic energy. Let's just pop that there. Okay, and all of that must add up to 0, right? Because there's no additional work in or work out. Remember, I said that initial velocity it may have been caused by some force earlier, but that force is gone now. So it still adds up to 0. So now we've just basically got an equation to solve, really. We've got minus 2gx minus 0.4g plus 4 plus 5x squared minus 0.2, and that's equal to 0. And oh, I've just spotted a mistake. Well done if you caught it before I said so. That kinetic energy is negative, remember, the change. So this one here is also minus. Okay, so minus 19.6x minus 0.4g gives us minus 3.92 minus 4. So in fact, let's just change that minus 3 to a minus 7.92. Minus 0.2 plus 5x squared equals 0. Again, let's just speed things up a bit and change that 7.92 to 8.1, having taken that 0.2 off. And we end up with the following. So 5x squared minus 19.6x minus 8.12. So I'm just effectively writing it in the standard form. And yes, that's it, that's correct. So the rest is just solve the quadratic equation, really. You're going to get two answers, presumably. I'll just check what they should be. So you will, in this case, end up with an x, let's write it here, x is equal to 4.298, or x equals minus 0.378. So by the same logic as in the previous question, previous example, we're going to ignore the negative, take the positive, and then just remember what we've originally been asked. What's the distance it travelled before first coming to rest? That's this distance with the question mark. So that's 0.2 added to that x. So it's 4.298 plus 0.2. So our final answer is 4.498. So that's with the 0.2 added on, meters. Okay, so a few questions for you to try. 2 on this slide and 1 on the next one. Have a go at these 2 first. You can pause the video now. Okay, and then once you've done the previous 2, have a go at this one. You can pause the video now.